Well, to be clear, the context of that Jensen touching was all the authors of the Transformer paper being on stage. But yes, thank you for having me here. I'm actually going to introduce some work we're literally publishing right now. It just went on GitHub and going to be on archive in the next couple of days. And just to introduce the idea, right? AI, from my perspective, is the last technology wave because effectively most of the work, if not all, from now on will be done either with AI or by AI directly, right? We already see this, the physics and chemistry Nobel Prizes are going to AI researchers. We see this, like effectively accelerating mathematics with AI tools. We see this across material design, and obviously in computer science, in development, in everything else, even making slides, right? All of this is now done with the use of AI. And so the challenge is like whoever controls the AI, whoever controls how you actually interacting with it controls everything in result, right? They can decide, if this country shouldn't be able to have access to it. They can decide that this specific actor or company or person shouldn't have access to it, or they can apply whatever filters and censorship and they want to. And this is kind of the current state, right? We have closed source AI that has a ton of challenges. Because you're effectively having a single party controlling access to what is a fundamentally changing technology. It's like if AOL controls the internet, right? And then we have the open source movement, right? People are building AI models and open sourcing them, which is amazing. The problem is it's completely unsustainable. As soon as you open source it, everybody else can now run it and you make no money off it. And stability was kind of a really good example of being one of the first ones to open source a really state-of-the-art model. And then they have a ton of trouble kind of financially to continue maintaining this pace and innovation. And so we kind of see that with every company that open sources it, have trouble continue the pace. So the solution that we kind of propose is a completely different model, right? It's a model where instead of AI controlling by a single company, you have AI that's optimized for the user's well-being, right? User-owned AI. And so this really builds on top of all the crypto values and kind of mission that Near Protocol, for example, has of ensuring that everybody has control of their data, assets, and power of choice. It also means that your AI becomes this universal interface, right, that interprets the internet and participation with others for you, right? It is your interface and it needs to be on your side. Like right now, when you go to google.com, you go to any of the products, they're not on your side. They're actually trying to make money off you, right? That's their business model. So we want to switch this and actually enable that what you're interacting with, what is kind of your direct counterparty in computing is on your side and is kind of optimized for your well-being and economic success. And obviously, this is not communism. We want everybody to actually make money of it because we need a capitalistic engine underneath to really power this. So, users, services, researchers, developers all need to be rewarded kind of proportionally to the value they're creating. Now, the question is how, right? This is really cool vision, but we either have a corporation that builds kind of for-profit models, or we have open source where people don't have resources to really develop anything. So what we introduce is this idea that if we can actually achieve few properties, we can build this user-owned AI. And so few of the properties that are really important is confidentiality and verifiability, right? Right now, when you go to the OpenAI, Anthropic, Google, anything else, right, you're effectively sharing your private data with some company and it goes somewhere. And so as we assume this AI model, this AI assistant is becoming more and more knowledgeable about you, presumably listening even to your conversations at all times because that will give it the most kind of context about you, we effectively losing more and more of our personality to these companies, which again, their incentives are to make money of that data, not to become, to kind of make you successful. So confidentiality, ensuring that your data only stays yours, and until you actually explicitly want to share it with someone, potentially in exchange for some value, should be the, the must for user-owned AI. And verifiability is another part because if you again, right now you're running OpenAI, it may be running this model, it may be running that model, it may be filtered some stuff on the answer, I mean, this is obviously happening with some other models where you see the answer and get rewritten by the post-processing. So you want to have effectively a way to verify that the answer you got is indeed coming from a model. Another kind of, I was scaring people about this about a year and a half ago, and now this is actually happening. People are introducing an add model directly into LLM output. So as it actually outputs tokens, instead of just outputting what data tells it, it literally can run an add and prioritize specific brands in your output. So those two things are extremely important for this user-owned AI vision. Now, how do we achieve this, right? We actually had a talk before that, which I missed part of it, so I don't, maybe some of these numbers need to be updated, but we obviously have ZKML. So ZKML is cool. It gives us verifiability. We know that model was run, but it doesn't give us confidentiality unless it's run on the local device, right, by the user. So if you have like a larger model that runs on some shared hardware, that hardware has access to everything that needs to be computed over, and it has a massive overhead. Consensus, okay, let's run all of the GPUs in the consensus and make this, verifiable. Again, great, but not confidential. Every single interaction, prompt, etc., goes on chain, and now everybody sees it. And you still need at least like 30 to 100 nodes to kind of consider the reasonable consensus. We have fully homomorphic encryption. It is confidential, which is great and verifiable, but it is massive overhead. Now there's quantization, there's a few different methods to like reduce this, but again, this is not yet production, and we haven't seen it really scaling at a level of like, you can run DeepSeek, you can run like 400B Llama. You can just run a local model, right? If it runs on a local machine, your data doesn't go anywhere, and it is verifiable because you ran it. Now, the problem is, assuming, world is mobile, 5 billion people on mobile devices, you can run about like 2 billion parameter model locally. That's about the limit right now. Now, this is improving. All of these numbers are improving, so that's good. And what we're left with is trusted execution environments, right? They give you confidentiality and verifiability. They have a very little overhead, about 5-7% for kind of AI compute. And there's an interesting guarantee that nobody else have given, which is that only this compute was done on this data, which is a really kind of additional benefit that you can use in different applications. Now, there is a potential for side channel attacks. I'm not going to say this is perfect solution in the world, but it is very reasonable for specifically machine learning, where you are piping a lot of data through the system, and even if you are side channeling attack and getting like few bits an hour or something out of the system, it's not going to actually allow you to get any private information. And if you do want to handle private keys and other stuff, there's additional methods to address that. So what's really interesting, there is something changed about like within last year, where we went from kind of a very custom built trust execution environment where you needed to write a different code and you needed to implement a very different system, to effectively now being able to run any virtual image of any operating system inside this execution environment, inside Secure Enclave, and not need to modify any code. So Intel has this called Trusted Domain Execution, TDX, AMD and ARM have as well versions of this. So this gives you an ability to effectively now just build a Docker container and just spin it up inside this execution environment and know that only this code was run on this data and only this thing was done. This also works now with NVIDIA GPUs starting from kind of second shipment of H100s. And so you now have an ability to plug in and run 8 H100 on a single machine with one Intel TDX CPU and have a full end-to-end AI inference model running for like 400B parameter model with 5-7% overhead, fully confidentially. Nobody's able to access what's happening inside, and verifiably that only this model was run on this data. So we have built with Follow Network a confidential virtual machine abstraction. So just so you don't need to think about like different hardware, there's how they're registered, there's different certificates that needs to be provisioned, etc. for verification. And so this abstraction allows you to effectively say, hey, I need a Docker that runs like with this hash of a Docker container, run it on some TE, and then when I call it, it will verify to me that only this Docker runs. And you can establish a TLS connection now and effectively have a full end-to-end confidential computation done through this. So this already enables a ton of interesting stuff. We have a whole new programming model for blockchain now, where instead of writing everything in a smart contract, you can actually build a Docker container and run it in the CVM, and then call things from your blockchain smart contract into CVM and get back response and verify that indeed it happened in this. Now for AI specifically, we need a few more primitives. First of all, if we are, again, having take an open source model, then anybody can run it, and there's no way to kind of do much. But you can actually have this primitive of a decentralized encrypted model, right? So instead of it's being open source or being kind of private and running on kind of some individual company computers, you can have an encrypted model weights that are stored in decentralized storage, and you can have the private key to decrypt it be stored inside CVM, inside confidential VM. And so when a new VM boots up, it can effectively exchange with any other existing confidential VM and get that key from it, verifying that indeed it came from one of these CVMs, right? So they can effectively establish a handshake saying, hey, I'm also running in TE, I'm also running the same Docker container, let's exchange the keys privately. And now I can go and decrypt this model and run it and do inference on it. And so for key storage, you want to use this concept of oblivious RAM to ensure that side channel attacks are not possible. So this primitive then gives us an ability now to say, there's an Alice who's like, hey, I want to run a private inference on this model. She establishes a payment channel through a smart contract, saying, hey, deposits whatever $10 of effectively your inference credits. And now with this can go to any CVM and say, hey, run this inference on this input, and here's a payment channel, effectively ID and signature for this transaction. Right, so this is happening fully, you establish payment channel once, and then every single inference happens fully off chain. You just sign on top of the response kind of as you're using it. So then, Bob is potentially untrusted party, is not able to see what happens. They just see there's a TLS connection happens inside CVM. They don't know what that is, from who that is, etc. Inside CVM, there's open channel that keeps track of all the payments, runs inference, and replies back with effectively, countersign that, hey, you use this much of this payment channel by running this model. This is many output tokens, this is many input tokens, and then here is the reply, right? Again, everything done through TLS of this specific confidential VM, right? They actually issue their own certificates. The cool thing is now both Bob, who provides hardware, and model developer who uploaded this model can get paid, right? Because this payment channel, when it gets closed, can distribute the payments proportionally to whatever was specified on the model when it was uploaded. And so you can have, there's the GPU cost, whatever, $1, $2 per hour, and there is a model developer gets something like 10 cents per million tokens, right? So all of that can be effectively embedded into the model weights when they encrypted and stored. So there's one missing piece, right? Because this requires actually finding a CVM and then being able to communicate with it. And importantly, if that CVM doesn't actually do anything, right? You have now a payment channel with someone who doesn't have, who doesn't have to kind of respond. Obviously, you can close payment channels, and there's a whole protocol around that. But there is an interesting concept of how do you even ensure responsiveness in the network, right? This is actually something that in distributed systems, frequently we overlook and kind of just okay, let's assume there's enough good nodes in the network to actually distribute blocks. We assume a lot of things. And so this is actually some problem we've been thinking a lot about, because It's pretty fundamental to consensus. It's fundamental to decentralized data storage. And it's really important in this case when you have effectively individual nodes doing the work. And you want to ensure that they're actually going to respond to you. And so we've developed a kind of a new overlay network, which works in a specific way to guarantee that you're either going to get a response from the node you're asking, or you're going to get a proof that one of the edges has been broken. And the breaking edge means somebody got slashed effectively. So this is a network effectively of relayers. You can think of them, routers that actually route the networking between different nodes. Each router with whoever it's connected has a payment channel, a small payment channel established that effectively ensures there's economic activity. Every packet sent has a payment attached to it. So this is actually incentivizes the bandwidth as well, which again, something on blockchain generally been dismissed. And if one of the nodes is not responding, there's a protocol effectively to break the edge, which if all of the edges with your node are broken, you effectively get kicked out from the system and you lose your initial stake. So this really enables, among other things, effectively Tor, right? Because you can onion your request from one node to another, and you have effectively fully incentivized, kind of private network that allows to really communicate with any of these nodes. But in our case, it allows us to have guarantees that if you're requesting some confidential VM to do something, either it will respond to you, and you can validate that the response is correct through a TLS certificate, or it will not respond, and somebody will get slashed. And so you can then reroute your request to another CVM. So in a way, this is actually a replacement to a fundamental TCP/IP, right? TCP/IP gives us guarantees that you'll get a response, like a ACK, on the networking side. So this is a really transport level protocol that actually introduces crypto economic incentives on this level. So let's put it together. Now we have a decentralized confidential machine learning cloud, right? Where you effectively have lots of these nodes running around. Some of them have GPU, some of them don't. They're running this confidential VM. And you effectively can go on-chain, fetch the nodes that are in this network, set up payment channels, both for the cloud, it's kind of for the networking and for the payment with the nodes. And you can now run either a simple LLM inference with a GPU node, or run an agent that goes itself and then runs on another GPU node the inference for the agent logic, right? So this creates kind of a effectively whole system that can run machine learning, AI, as well as just regular, Python, TypeScript, whatever, Rust code, etc., in fully end-to-end verifiable confidential way. You can ensure that, if some nodes kind of get disconnected from the system or start censoring, they get kicked out. You can ensure that they can only do the things you requested them to do with your data. They are not able to store it. They're not able to maintain it. There's effectively one Docker container published that everybody can inspect how it runs, that loads the models and responds to these requests. And so this is effectively a system that allows to really pull together all of the requirements we have for kind of a modern user-owned AI and enable that through kind of a whole host of protocols really to kind of deliver this result. So just to kind of leave you with this idea, right? Okay, cool. So this is great. This enables now developers who build their model, instead of open sourcing it, they can effectively encrypt it and upload it into this cloud and get monetization. This allows existing open source models to effectively be uploaded there, and you now have a verifiability that you run that model without needing to trust any specific provider. Now the thing is, it's still missing the piece where, okay, how do I know that the model I'm running has not been poisoned, right? So for those who are not familiar, there's this concept of sleeper agents. So you can fine tune a model in a specific way that at a given time or a given conditions, it will, for example, insert something malicious into your output, right? To give you a very specific example, as you're typing in Cursor, instead of import transformers, it will say import transformers. right? Which is a malicious library that is, stealing all your data. So how do we know this didn't happen, right? Like everything I was talking about was about inference. Well, you can actually build with the same now cloud a fully community-owned model, right? So let's imagine we have a DAO that comes together and says, hey, we want to build this amazing community-owned models. We're going to launch a token. We're going to use it to fundraise or to distribute it to the people as reward. And then we're going to use that to prepare data, model training, and kind of algorithm improvement. And then we're going to run the training itself inside this cloud, right? Which again, this gives you really interesting guarantees because no single party will ever see the weights, right? There was no single computer that it had seen in clear text the weights. Now, everybody can verify that this code and this data actually went in to train this model, right? I mean, there's partitioning and everything that needs to happen, but in general, this model outcome is a production of this code and this data. And so now if anybody can inspect and see that there's no kind of malicious injections and biases in this data. And finally, this resulted model, it's encrypted, and now everybody can use it inside the CML cloud for inference, fine-tuning, and other experiments. So effectively, everything you do, usually with open source model, there's no kind of any additional restrictions except that you need to pay for using it. And so DAO now can make money to really reinvest them back into new models or allocate back to the token holders. So you have now a full economic model from training to inference and fine-tuning to feedback into the either next generation of models or a way to kind of repay back the initial investors. So this is really how kind of like this fundamental technology now enables community-owned models and really enables this community-owned future. So if you're interested to learn more, we have just two papers. One is proof of response, which is kind of overlay network, and one is decentralized confidential machine learning cloud. They're just coming out. So check it out. Would love your feedback and responses. Obviously, this is still work in progress. And yeah, thank you. Follow me. And yeah, talk on Twitter. Thank you.
All right, thank you so much. Are you game to take a couple questions?
Sure,
yeah.
yeah.
Are any? Yeah? Okay, perfect. So, okay, yeah, there's going to be a ton of questions. I'm so excited for this. Go ahead, just talk into the mic.
Okay, so you're using TEs. Who are the roots of trust of those TEs?
Yeah, so for each hardware, right, there is the manufacturer that is the root of trust. And so you can effectively have Intel, or ARM, and then you have NVIDIA. And then what we do, we have effectively on-chain registry of all of this, so you don't need to go to Intel every time. So if Intel gets compromised later, you don't need to kind of rely on that. But indeed, yes, the whole system is relying on the manufacturers, and that is not great, but it is very practical and works right now.
Yeah, kind of. I have two questions. One is follow-up on that. So one is that, so essentially when you use H100, as far as I know, the confidential compute can be only done with one VM attached with it right now. And that only should work with Intel's TDX version, so it extends the root of trust, right? And Milan Plus processors. Those two are highly expensive processors. So have you looked at what are the cost overhead of running the same model on H100 with CC, with confidential compute and without? So that's the first question. And the second one was that in your slide number 12, you talked about trigger attacks, right? Like attacks on machine learning models like LLMs, where it produces. So the threat model for those are that in the pre-training data, we have poison data sets, which specifically has triggers. I'm only talking about trigger attack. So how does this we know that, okay, anybody who is training on their own data, yes, we know who has those data and what is coming out. But most of the training probably will work on pre-trained models, and you fine-tune on that. That pre-trained model might already have the trigger embed, and that is there a better way to detect that apart from what Hugging Face is already doing?
Yeah, so first question, the cost. Yeah, so the TDX is only available on Intel 5th generation, which is about like $1,000 per CPU, which is expensive indeed. The thing is, like, if you're buying 8 H100s, each costing $30,000 plus NVIDIA Link, you probably can spruce over for $1,000 CPU to get this going. So, and then we have effectively Blackwell coming, which offers intercluster confidentiality. And so, if you're buying Blackwells, which are going to be like even more expensive, and setting up a cluster with them, you may as well buy the most modern CPU. So the cost overhead is, not that much compared to GPUs already. And then if you're just talking about the CPU, like we have obviously some CPU nodes. Well, the benefit is those 5th generation CPUs have like 128 cores or something, so you can run a lot of them. So it's worth the cost. The question about like, hey, are there already trigger attacks on existing data? First of all, probably somebody is maliciously poisoning all of the internet right now, because like that's the thing to do if I was malicious. And so the point of this community-owned model, which not on screen anymore, was indeed to do a pre-training run, where you actually first have community to filter out data in a very specific ways, right, where we all agree that this is actually the criteria. And then we use that data now to train, and now everybody has guarantees that this data used for training. It is inexpensive, but I mean, as DeepSeek now shown, it's actually not that expensive. Probably this is not practical yet until Blackwell. And so I think that as soon as the clusters of Blackwells are going to be available, this is going to be a really kind of powerful way to do a pre-training.
Okay, we have time for one, maybe two more questions, so you're up next.
Yeah, so what do you think about the security and safety of these models and AI agents? And the second question I have, like, do you think like RL could be a good technique to find even a model in future, because data might be limited in future?
Yeah, so I mean, the security and safety obviously depends on the model and on how it was trained and built. There's few things that we are working on. One is we actually have a bounty for an audit agent, which is designed to audit agents. So, I mean, I haven't talked about it, but we have a Near AI hosting platform built on top of this cloud where you can host your agents and models. And so on this platform, when you upload an agent, we're going to be running effectively checks with AI auditor to ensure that your AI agent itself is not trying to, steal everybody's data. Now, on top of that, I mean, this approach would be to train actually, safer models. Finally, the longer term research we're working on is a concept of formal verification. So the reality is, like, it doesn't matter how much you check, right? How many security audits you do, there's going to be always still bugs and issues in any code or any system. And so the only way to effectively defend against that is to have a formal mathematical proof against the specific conditions that you care about. So to give you like a simplified example, if you're putting money into Uniswap, the only thing you care about is that when you withdraw them, that the production of the withdraw money will be not less than what you put in. That's a precondition to care about. You really don't care about anything else. And so what you want is when you're putting, like, in the transaction you're putting money in, that there is a formal verification check that happens on this precondition. So that is a system that you can apply for AI agents as well, because it doesn't matter what model thinks, right? It doesn't matter what activations happen. What matters is what it does. And if it can prove to you that it's not going to do anything that is not satisfying your requirements, well, the execution will fail, right? So that's a system that we're actually building long-term to really ensure, and it can run inside this directly CVMs to ensure that, like, as you connect to them, they guarantee this execution.
Okay, thank you so much. I know there's probably a lot more questions, but we're at time. Ilia, thank you so much. That was an amazing talk, and really appreciate you coming. Round of applause for Ilia, everybody. Yeah, thanks. Thank you, really appreciate it.